This video is entitled The Derivative and the Tangent Line Problem. So I'm going to start out here and we're going to take a look at this graph f of x. And we're going to define something called a secant line. A secant, I believe, is Latin for cut. Anyway, a secant line is a straight line drawn between any 2 points on a graph. Anywhere, whatever the points of interest are. Now come down here and we're going to label the first point in function notation CF of C. Now this, the Larson textbook and many others use delta x for the change in x from the first. Delta generally means change whenever you use it in many applications. That little triangle is called delta. Delta x to represent the change from the first x to the second x. I like to use h. There's books that use h also, but I like to use h. It's a lot simpler to use than delta x, and I'll show you why in a little bit. So if this point's denoted as CF of C, and then h is the distance between the two x's, that would make the next x C plus h. So it would be C plus h, F of C plus h. Now the slope of that secant line is straightforward algebra measurement, y2 minus y1 over x2 minus x1. But we're going to use the notation as given above to define this secant line. So I'm using the subscript secant here, and of course our usual m for slope. So msec is f of c plus h minus f of c over c plus h minus c. And then notice in the denominator that the c's would cancel, nothing happens on top. And it would simplify to being f of c plus h minus f of c divided by h. Now that leads us to the concept of what's called a tangent line. Now just imagine, if you will, if we took the second point and kind of moved it closer and closer and closer and closer and closer till it got near that first point. Real close without touching it. We'll talk about why it can't touch here in just a minute, but just picture those close points being infinitely close. And then you would have this line that sort of represents the slope of those 2 points that are basically the same point. We call that a tangent line. Now graphically, a tangent line is going to behave, that means in the immediate neighborhood of the point where you're trying to find the slope of the tangent line, it's only going to touch right there and only there. It's not going to. Now that doesn't mean like if this graph keeps going on and on and on, the tangent line can hit it farther out down the road. That's all right. And same thing if this graph turned back around and hit it again. But in the immediate neighborhood, it would look like that. So I guess point being is you'd never have a tangent line that looked, like this, where it kind of cuts through like that. That would not be a tangent line. So anyway, so we're essentially moving those 2 points infinitely close together. And suppose we want to find the slope of the tangent line, which is also known as the slope of the graph at x equals c. So this is the first time in calculus, is the first time you're going to encounter finding the slope at a point. Anywhere else you would have had this, it would have been like the slope of the secant line, slope between 2 points. This is the slope at a single point. And the problem, let's say if you take this formula right here and you want to calculate the slope between 2 points that are essentially the same point, that would mean the distance between them, h, would be 0. And that gives us a big mathematical problem right up here, because dividing by 0 is never allowed. So the way we do that is to allow this point to get infinitely close without touching. Goes back to previous chapter. We can use the concept of a limit. A limit can allow you to get close to that number but without touching it. So now we're saying take the limit of that slope as h approaches 0. Doesn't mean it equals 0, approaches 0. So you're assuming that they're getting so infinitely close that they might as well be the same thing. So that's the difference here. So the secant line slope is this formula but without the limit in front of it. But the tangent line slope is the limit equation. All right, so let's take a look at this. We're going to find the slope of the tangent line to the graph of the function at the given point. They're telling us that f of x equals 5 minus x squared. And we have the point 3, negative 4. Now keep in mind, they really only have to give you the x value, because any function, remember f of x is basically y. So I could have plugged that 3 in there and got 5 minus 9 and got that negative 4. So only the x that we're interested in has to be given to you. So we're going to evaluate this expression right here. So the c is 3. So f of c plus h minus f of c over h, where the limit as h goes to 0, can then be c is replaced by 3 because that's our x of interest in this problem. So now we want to evaluate this. Now the trickiest part about this is the f of 3 plus h. Now f of 3, obviously you could plug it back in, but if you realize that f of 3 just means what is y when x equals 3, since we already have it, it's negative 4, but if you plugged it in, you'd also get negative 4. So that being said, I'm going to, remember to evaluate a function, when you're evaluating f of something, remember you're just taking whatever that something is and replacing it everywhere you see an x. In this case, we only have one x. So I'm taking the 3 plus h, putting it in there for that x, and I'm coming right down here like so, and there it is. So that was where x was. So 5 minus, and then quantity 3 plus h squared. Okay, very important we don't make algebra mistakes here. That's 3. You got to square that out. You don't have to do it in your head, but you can FOIL it if you need to. But 3 plus h, quantity squared, is not 9 plus h squared. There's another term in there. That's 2/3 of the right answer, but it's got a 6h in there also. So we have 5 minus and then 9 plus 6h plus h squared. Now, that all follows a minus sign, so you have to be careful. That means the negative would go all the way through the parentheses. And you can take 5 minus 9, leaves a negative 4, and you have a negative 6h and then minus h squared. So now we're going to come back and evaluate the limit. So we have the limit as h approaches 0. So you see the first part right here is this right here. And then some minus f of 3, which is negative 4. Now what's going to be very important in these problems is that any term that does not have an h will have to cancel. So those negative 4s do cancel. And because that's very important, because for this to have an answer, because we can't divide by 0, we need to be able to factor out an h to where we can cancel that h on the bottom, and therefore we don't have the 0 on the bottom anymore. Just like, we've done factoring and canceling with other types of limits. So these two terms, minus 6h minus h squared, they share an h. Factor out the h, and then cancel the h's, and you're left with negative 6 minus h. Insert the 0 for the h, and you would have negative 6. Now, negative 6 would be the slope of that tangent line. Jump ahead for a second. Okay. Now, you'll see here in a minute how I got this. So the negative 6 was a slope, and we'll talk about how to get the 14 here shortly, but I went ahead and did it. So you see I graphed the original function, 5 minus x squared, and then the tangent line, which does have a slope of negative 6, is negative 6x plus 14. So I'm kind of jumping jumping a little bit ahead. But anyway, that's a good tangent line. It's coming there, and there's the point of interest right there, the 3, negative 4. And it's kind of running alongside it, but if we really zoomed in on it, it would just be touching it only at that point. And then the blue parabola would keep coming down, like this, and then it'll come down, and then the red line will start fading away from it. They'll go their separate ways. So that's a very good tangent line. But like I said, the main thing is, we're not trying to analyze this to death, but you certainly want to make sure that, if this was your point of interest, but like I said, okay, you wouldn't want a tangent line going, like right through there or something. No good. Well, I should have made it go through the point there. I just don't want to mess up that dot I already have, but I'll go ahead and do it so I can undo it. So I wouldn't want it going like that. That would be no good. Now suppose that instead of just using a specific value for C, like we did with this one, with C being 3, what if we want to find it as a generic function of x, meaning that if we solve this in terms of x, then you could go back and quickly evaluate it for any particular x that you want. So that's pretty convenient. So if you solve it in terms of x, then I could go back and say, well, what if x was -3, like we just did, or +3, excuse me, or then -3. I could quickly plug it into this new answer without having to go back and do this every time, without having to do this process right here. Like if you did 3, and you want to do -3, you want to do -4, that would be pretty time consuming if you had to do that every time. So there's a big advantage for getting it just in terms of x, and there's also an important mathematical reason for doing this also. Lower this down. Let's see. All right, so now I'm going to find the limit as f of x plus h of that same function, and then we're going to, so I'm still working with the 5 minus x squared. So x plus h, so 5 minus x plus h squared. So you square that out, FOIL it out, it'll be x squared plus 2xh plus h squared, distribute the negative. So now we're going to evaluate the limit. So everything in the first set of parentheses, see there's no like terms here, so nothing combines or anything like that. You're left with this stuff right here, that's the f of x plus h. Now f of x is always just your original function. So the right side of that will always be whatever this is right here. So it's 5 minus x squared. So now it's very important. Now we have x's and h's mixed up together here. That's okay. It's very important that any term that does not contain an h should cancel algebraically properly. It can have both an x and an h, like this term right here, but it can't be an x. So that's why the 5's cancel and the negative x squareds must cancel, and they do. I'm not just canceling because I want to. They actually do cancel. So now you can see that even with that x there, that's okay because it has an h. We factor out an h. The h is canceled. That's the key, is canceling that h on the bottom. And then now, see, this is the limit as h goes to 0. So you might think, I know we're used to dealing with limits from the previous chapter, plugging the number in for x. But always remember, this is as h goes to 0. So the 0 goes in for the h. So you're left with a negative 2x. So you then can come up with any slope, tangent slope, for any x, like super quick. So for example, if we took that first one we did way back up here, see the c, which was the x, was 3, and we got -6 as the answer, which was correct. But look what happens when you plug 3 into this negative 2x. You're going to get -6, aren't you? So, but now, see, so look at this. So I could quickly come up with 2 other values, like -4 or 5, without doing that other process. I would just plug them right in for x. So -2 times 4 is -8. I'm sorry, -2 times -4 is +8. If it would have been +4, I was right, but it's -4. And then put in +5, you'll get -10. Now you see, this is where I crossed out these delta x's because I like to use h instead of delta x. And the main reason I do that is because if you start doing this process up here, and I've helped students with this before, like in tutoring sessions and things, and I've helped them, and you start taking like x and multiplying it times delta. Like here's an example, the x times the h. I've seen people get confused with x and then having that as a delta x like this, and somehow they might want to think that that means this. It does not mean this, but it looks like it could. But see, the problem is that it's the delta x, the delta and the x together are representing one variable, so you can't multiply that. So you see, I think you can see now why that could be a little confusing, maybe for some people. So, but there's no problem if you got an x and an h multiplied together, then you know that those are separate variables. But the delta x being a separate variable could be confusing. Now, this limit that we just found now has a name, and a very important name throughout the use of calculus: the derivative of a function. The derivative, and I'll talk about the notation, is that limit as h goes to 0 of f of x plus h minus f of x all over h, provided the limit does exist. Now the f with the little single quote, we call that f prime of x. So you'll hear me say f prime. Now the process of finding the derivative is called differentiation. Now there's different kinds of notation. It's just, you want to be able to recognize all the different kinds. It's not like it's a question you would have to answer on a test, At least I wouldn't ask, name different forms of the derivative notation. You'll see me use a variety of these. F prime of x is fine. If the function's defined as y equals, you can use y prime. dy dx means the derivative of y with respect to x, meaning your variable is x. And then just d dx of whatever your function is. That's also acceptable. So those are all just different notations of accomplishing the same goal here. So now we have so we have derivative, differentiation, differentiable. A function is differentiable at x if the derivative exists at x, and it's differentiable in an open interval a to b if it's differentiable at every point in the interval. And that's one thing we'll talk about a little later. I'm not sure if it's in this section or a different video, but derivatives don't exist at the actual endpoint. So this it can only be differentiable in an open interval. It can't be differentiable in any kind of closed interval. So one function, obviously the derivative is to calculate the slope of the tangent line at a given point. And that's what we've been doing here. And we'll look at, you see like rates of change is going to be something we'll learn what the derivative is for. Now find the derivative using the limit process. Yes, if you've studied calculus before, and then we're going to see some better rules how to do this in later sections, but I might could find some way to slip this f of x plus h minus f of x maybe on a test or something, so it's good to know how to do it. Especially, a face-to-face class, I like to have them write this out. Online test, it might be a way I can sort of get it in there somehow too. So, but most of the time we're not going to be using this process. We're going to be using the shortcut rules we're going to learn, I believe, in the next section. So literally to find f of x plus h, you replace x plus h everywhere you see an x right here. So you put an x plus h squared and then x plus h right there. And you just work all this out. So we have x plus h squared is x squared plus 2x plus h squared times 5. And then once again distribute the negative through the parentheses. So it's negative 7x minus 7h and then the plus 2. distribute by 5, and you actually just have 6 terms there, no like terms. So there's nothing to combine. And remember, the f of x will just be your original function right there, which that's going to always have to cancel. The original function will always cancel because there's no, every term has to have an h. You see, there's the f of x, and they cancel, and there are the terms they cancel with. So we're interested in looking to see what's left. What are the remaining terms? And you see that I'm left with a 10xh plus 5h squared minus 7h. The limit as h goes to 0. You factor out an h and cancel it. Then you reinsert the 0 in there for h. So it makes that term go away. So it's 10x minus 7. Now, if you're in a face-to-face class, and at least my class, and a lot of instructors would probably feel the same way, I would imagine, but you know, the notation is very important here. You got to keep that limit notation with each step. We didn't do too many steps there, but keep that limit in front of it. You can't just start doing all this stuff without the limit. And using derivative notation is very important also. I know Maple doesn't do it here. I did ddx of that and see what it spit out the answer. Maple doesn't do it, and I don't blame Maple for not programming it to do it. That's fine. But the student needs to know that a derivative is actually a function. You know, so it's a function that you're evaluating, so it's got to have notation in front of it. So, albeit whether it's like f prime or y prime or something, it's not really correct. You know, see, so I'm saying that equals 10x minus 7, but that also means, maybe I should put that in pink also, I guess, couldn't I? But yeah. So really, that f prime of x goes with that 10x minus 7. But with all those equal signs, I kind of have it linked together anyway. All right, so you see Stewie's kind of yelling out here. Stewie's the alter ego here that fusses at you when you make sure you don't make any little mistakes or anything. So Stewie's harping on that on that notation issue. Now let's see. So based on this previous example, what if we wanted to find then the derivative at -3 and then the derivative at +4? So I'd put in 10x minus 7. I'd put in -3. I'll get -37. I'll put in 4. I'll get 33. And remember, from what we've learned a little while ago, is that those are also then the slopes of the tangent lines at that point. So obviously very steep slopes, both positive and negative. But yeah, so those are those are still the slopes of the tangent lines. Now, how about this one? F of x equals 3 of x. We're going to do the limit process here. So when we evaluate f of x plus h, so all you're doing is putting in x plus h in for x. I see people really with sometimes their algebra skills are not so good, and they start coming up with some crazy stuff here. But you put in x plus h where there's an h, and then f of x will be 3 over x. So you can't do anything with that just yet, but you want to get this out of complex fraction form. So I'm multiplying top and bottom by x times x plus h, and then the bottom by x times x plus h, because that's the common denominator. So you see that's going to get it down into one fraction. So we'll have these x plus h's will cancel. I have 3 times x. And then I have minus 3 times x plus h. And then the bottom, don't do anything other than just write it like I did here. Don't distribute. Because the whole idea is we're trying to get rid of that h, you know, so don't, if you distribute, you'll just have to turn around and factor it back out. So it's kind of a waste of time. So, so leave it as is, and then distribute. The negative goes through there. Don't forget about the negative. So it leaves 3x minus 3h. Okay, anything without, in the numerator, it doesn't contain an h, should cancel, and it does. The 3x's cancel. And now then we have a -3 times h, so therefore since it's multiplied, and that's multiplied, h times all that. So because they're multiplied, I can cancel. In other words, you could not cancel with the h in the parentheses there, but I can cancel those two h's where the blue lines are. And then, if I reinsert 0, all I'm left with on top is a -3. I put in 0 for h, I would just have x times x on the bottom, and you get -3 over x squared. And you see Maple agrees with that. Hard to see that negative, but it's there. Maple likes that. There it is. And then, of course, find the tangent slopes at -3, 0, and 1. That's the same as saying find f prime of -3, f prime of 0, f prime of 1. And f prime of -3 gives you a slope value of -1/3. So you see right there, okay, that looks about right for a slope of -1/3. F prime of 0 is undefined. Can't divide by 0, so there's really no tangent slope. And actually, that makes sense because the graph itself is not even defined at -1. I mean, at 0. The graph's, there's a vertical asymptote there. And f prime of 1, put in 1, you'll get -3, so that's this line right over here. Yeah, okay, there's definitely a negative slope for sure. A lot steeper than that one, so -3, that looks good. All right, here's one, f of x equals the square root of x using the same limit process. And we've seen this kind of deal before. So now you have so you take the square root of x plus h minus the square root of x. And we did these kind of radical limits in a previous section, and you have to conjugate the radical. So we multiply top and bottom by the square root of x plus h plus square root of x, top and bottom. So that kind of simplifies the numerator. I know I kind of combined a couple of steps in one here, but I'll explain what I did. So when you multiply this, you don't have to even FOIL, because you just have the square root of x plus h times the square root of x plus h, which will just leave x plus h, and then square root of x times square root of x is x with a minus between them. So you have x minus x, because anything without an h has to cancel. So you see, basically what happened here is the red part cancels first. The x's cancel. But then now I have an h on top by itself, so it will cancel with this h on bottom, but leave a 1 on top, and then no h. Then you reinsert the 0, so you put a 0 in there, and you have 1 over the square root of x plus the square root of x, which would be 1 over 2 square root of x. I certainly don't care about rationalizing the denominator. Some other instructor might, but I certainly wouldn't. Differentiability and continuity. Let's see how they relate together. So first thing is the derivative is absolutely undefined at any discontinuity, which the two examples, the example before the last one is the one that had that vertical asymptote. Anywhere if there's a hole or the graph separates, and it's f prime of 2 would be undefined, so I made it 2. So might look like the first one. You could draw the horizontal or draw a tangent line there, but you can't. You can't have a tangent line at a hole. But however, there are some cases where the graph might be continuous, yet the derivative still does not exist. So in other words, being continuous does not guarantee every point will be differentiable. Endpoints. Endpoints are the tangent slope is undefined, because technically you can almost have like infinite tangent slopes, because it looks like, there's lots of places you could draw tangent, there or here or there, so the fact that there's not one unique answer pretty much means there's no tangent line. So the endpoint, but the graph would still be considered continuous. As long as there's a solid dot there, the graph is continuous, but the derivative is undefined. So any endpoint, the derivative is undefined, whether it be like this one, that just comes from the nature of the function, or if it's a man-made endpoint. Maybe we put in a specific closed interval. So man-made, woman-made, endpoint, whatever you got there. It's an endpoint, the derivative is undefined. Vertical tangents, those are a little trickier to see graphically. But like I said, I don't like to show graphs on a vertical tangent in the test, but I like to show the other ones. But they'll come about if you know what the derivative of the functions are. Now, that just means that the graph is actually continuous, but if you have a point in there to where the tangent slope's perfectly vertical, undefined, because slopes of vertical lines are undefined. So therefore, if the tangent line is vertical, there you have it. Now we don't know how to come up with this derivative yet, so you'll just have to trust me. I guess I could have put it in maple, but that's all right. Now, I'm not going to do it now, but it's right. You have to trust me on that for now, and then you'll be able to verify it yourself later. But notice that if you put 1 into the original function, you're okay. You get y equals 0 right there. But if you put 1 into the derivative, you have divide by 0, don't you? Because you have 0 right there. So therefore, the derivative is undefined. So there it is mathematically in addition to graphically. Sharp points. Anywhere the graph forms an extreme sharp point. Now there is such a concept, I don't really get into it, but there is such a concept as, we've seen left and right limits, of course, but left and right derivatives. And actually the slopes need to be approaching the same value from both directions, and I'll show you that's why it doesn't work for a sharp point like it does for a smooth. See, like this one, as this graph comes down, you got a sort of negative slope, and then red one, then coming from the other way, they're approaching the same slope. They're working there. Let's just say that's the point of interest right there. They're approaching that same slope from both sides. So that's why that's okay. But this one's not, because this slope coming down is always going to be -1, and the other slope is going to be +1, so they're not really merging into the same slope. So that's the reason why the sharp points are undefined. Now this absolute value is a little bit trickier, but the next one I can show you mathematically, this function x minus 1 to the 2/3. Notice this derivative, which like I said, you'll know how to do eventually, but it's would be undefined if you put 1 in there, but for the same reason. The slopes are not approaching the same value from both sides. That's why the graph kind of has to be doing something like that or like that. So the slopes can approach each other from both sides. Okay. So those are the keys. So we had sharp points, vertical tangents, and endpoints. Let's look at this theorem. Differentiability implies continuity. Let's see what that's all about. This says that if f is differentiable at x equals c, then f would have to have been continuous at x equals c. The next part of this says if f is not continuous at x equals c, then f is not differentiable at x equals c. So that's why, these arguments with if-then versus the concept of if and only if, which I use that terminology on the video for infinite limits. I'm sorry, one-sided limits and continuity. The if and only if means the argument works both ways. So, but it does not here. If-then does not mean that. So if differentiable, then, but if you know that, then for sure it's continuous. But the other way around is not true. And we just showed on the last page that 3 examples where it could be continuous at the point, but yet it was not differentiable. However, if the graph is not continuous, which was, we had that right up here, right? Oh, yeah, here. So if you can't, if you know it's not continuous, then for sure it's not differentiable. I use this notation from a logic class I took a long time ago. I don't remember all the details. I remember I enjoyed the class, but I think logic would be an excellent class. Well, certainly for, like computer science majors and whatnot, but I think anybody can make use out of it. But this little symbol, this tilde symbol, actually means not. But logically, if you have an argument that says if A, then B is, if A implies B for sure, you can't say B implies A, but it's interesting that you can say, though, that not B, B being false, will imply that A is false. And that's exactly what's happening right up here with these two rules. All right. Now this graph, question's asking on this graph, list the values where f is not differentiable. Now you can assume, we're in an open interval, so the fact that these arrows are going on and on and on, don't worry about that. They're not, only if it was clear, only if they made this clear that this was a, well, I added the arrows because on a calculator graph you can't always tell, but I would clearly mark it if it was sharp points. So if you assume this graph's going on and on forever, then you don't worry about that. So you look at other issues. So here it is. For this one, it would be these two sharp points right there. -3, +3. So there's two places where it's not differentiable, but then I mentioned over here, though, however, the graph is continuous everywhere. That is true. But there's two spots where you can't take the derivative because of the sharp points. It's making sharp points there. Now, list the values where f is not differentiable. Ah, yes, this is our friend that if you watch the other video, if you didn't one of the other videos, I call this one the, I'm not exactly an artist, but call this one the sad face graph. Maybe it needs a nose right there. So there we go. It looks sad. It should be happy because calculus is fun. But you see the two vertical asymptotes would be where it's not differentiable. And it's also not continuous. Also at those same points. In this case, it's both. So this one's telling us to list the values of x where the graph is not continuous and not differentiable. So, one thing about this list is, you're going to have either the same amount of numbers or you'll have more in the not differentiable than you will in the not continuous. You could not have a list where there were more not continuous answers than there were not differentiable, because if it's not continuous, then it's going to be not differentiable. So that means all the not differentiables will include the not continuous numbers. There can't be more in the not continuous. But there can be some that are not differentiable that are continuous that we just learned. So the only place this graph's not continuous is here at this -2, and then right there where that hole is. Even though there's a dot right there, that just means the function exists, but technically that's not continuous because it can't go through the hole there. So those two for sure are on your not differentiable list. However, there are others that are not differentiable. So this one, notice I definitely made an end point there on purpose for that one. I made an arrow on that one. So the fact there's an endpoint here, 1, 2, 3, 4, 5 at -5, I didn't list those in because they're not in interval form. You can list them in the order, doesn't matter. But -5, not differentiable. And then +3 up here, we got a sharp point. So at x equals 3, we got a sharp point. So not differentiable there either. So right, that concludes